as looking at f of x, y is equal to the tangent inverse of absolute value of x plus the absolute value of y over x squared plus y squared. Is that correct? Correctly? Okay. So we have this, and what we want to do is we wanted to take a look at this using polar form. Okay, so if we take a look at this, all right, so we are going to have, we're going to do the limit as xy approaches 0, 0, okay, of the tangent inverse of absolute value of x plus absolute value of y over x squared plus y squared. Okay, so if we convert it to polar, we're going to have the tangent inverse of. Okay, so in place of x, we can look at the absolute value of r cosine of theta. In place of y, we can take a look at r sine of theta. And this is going to be over x squared plus y squared is equal to r squared. Okay. All right. So what we need to do to get this completely flipped over, we're going to let me think of the best approach for this. Oops. So, all right, so let's do a rewrite first. So this is going to be the same thing as saying the tangent inverse of. All right, so r is in both for the things, so I'm going to pull out the absolute value of r, and that's going to leave me with the following. It's going to leave me with the absolute value of the cosine of theta plus the absolute value of sine of theta. And then this is going to be over r squared. So this can be rewritten as the tangent inverse of. All right. So what we can do is essentially you can cancel this and this. So you can look at it as the following: the absolute value of the cosine of theta plus the absolute value of the sine of theta. And this is going to be over basically absolute value of r. Okay. Now, what we're going to do is to look at the limit in two forms. Okay. So the first form, we're going to take a look at the as r approaches 0 from the right. Okay. So if we look at this, so we look at the limit as r approaches 0 from the right of the tangent inverse of absolute value of cosine of theta plus absolute value of sine of theta over absolute value of r. Okay, so if you take a look at this, if we get close to 0 from the right, we're going to end up with the tangent inverse of the absolute value of cosine theta plus absolute value of sine theta over, we're going to have something really close to 0 but positive. Okay, so basically my question to you is, what is happening to this expression? So what is that expression going toward?
Indeterminate form, no?
Hold on one second. Say that again.
Oh, is that in indeterminate form? No?
It's not in indeterminate form, but let's think of it. Okay, so we've got the absolute value of cosine of theta plus the absolute value of sine of theta over 0 positive. So what do you think is happening to this expression? It's approaching what? It won't be 0 or 0. And let's keep in mind that as far as sine theta and cosine theta, really, if you think about it, no matter what's the max they're going to be. So what's the max cosine theta is going to be? So what's the largest that cosine can be? What? Plus, what's the largest sine can be? 1. Then we got it over 0 positive. So what is that going toward? As this gets closer and closer to 0, what's happening to this whole fraction? Yeah, it's going to infinity. So you're doing the tangent inverse of infinity. Well, what is the tangent inverse of infinity?
Is that pi over 2?
Right, it's pi over 2. All right, so now let's look when r is approaching from the 0 from the left. So again, we're going to have the tangent inverse of the absolute value of cosine of theta plus absolute value of sine of theta over the absolute value of r. Okay, so really this is going to be the tangent inverse of, again, as far as this is concerned, the numerator, it's the largest it's going to be is what? 2 over. Now for the denominator, that's going to be 0, but it's going to be what?
Negative?
Well, let's think about it. We're doing the absolute value of it, so it's going to be what?
Zero.
What's the absolute value of 0 negative? 0 positive. Okay. So this is going to be the tangent inverse of, well, what is this going to?
Infinity.
Infinity. And what's the tangent inverse of infinity?
I/2.
So since the left and right hand limits are approaching the exact same value, that's why for this particular problem, the limit as this approaches 0 is equal to pi over 2. Any questions? All right. Any other questions? Okay. So what we're going to do today is to move into kind of our last section for as far as material is concerned for the midterm. And the last section we're going to deal with is going to be the chain rule. Okay. All right. And I'm not going to write that initial page of notes up. So let me put that up real quick. All right. So if we take a look at the first page, oops, and just kind of look at the notes and everything. All right, so the first thing we have is this, all right? So we have that the chain rule for functions of two variables, we can say that if w is equal to f of x, y, where has a continuous partial derivative, so the partial of f in respect to x, partial of f in respect to y, and if x is equal to x of t, y is equal to y of t, excuse me, are differential functions of t, then the composition of f w equal f of x of t, comma y of t is a differential function of t, and the derivative in respect to derivative of w in respect to t is equal to the partial in respect to x of the function x of t, comma y of t, times x prime of t, plus, then we're going to do the partial of f in respect to y of x of t, comma y of t, times the derivative of y sub t. Okay? Or we can write it as this: dwt is equal to the partial of w in respect to x times dx dt plus the partial of w in respect to y times dy dt. Okay. Next, let's take a look at the chain rule for functions of three independent variables. It says if w is equal to f of x, y, and z is differentiable, and x, y, z are differential functions of t, where w is differential function of t, and that the derivative of w in respect to t is equal to the partial of w in respect to x times the derivative of x in respect to t, plus the partial of w in respect to y times the derivative of y in respect to t plus the partial of w in respect to z times the derivative of z in respect to t. So if you look at this, it looks this is the same as this. Okay, it's just that when you start introducing more variables, you've got more pieces that you got to do. Okay. All right. Next, the chain rule for 2 independent variables and 3 intermediate variables. So suppose that w is equal to f of x, y, z, x is equal to g of rs, y is equal to h of rs, and z is equal to k of rs. If all 4 functions are differentiable, then w has partial derivatives with respect to r and s given by the formula. So dw dr is equal to the partial of w in respect to x times the partial of x in respect to r plus the partial of w in respect to y times the partial of y in respect to r plus the partial of z, partial of w in respect to z times the partial of z in respect to r. If I want to find dw ds, it's the partial of w in respect to x times partial of x in respect to s plus partial of w in respect to y times partial of y in respect to s plus the partial of w in respect to z times the partial of z in respect to w. Okay. Next, our formula for doing implicit differentiation. So suppose that f of xy is differential and that the equation f of xy is equal to 0. Now, this is a key point that it must be in this form here. F of xy must be equal to 0 in order to use this rule. So, and defined as y as differential function of x. Then at any point where the partial of f in respect to y is not equal to 0, then we can say that dy dx is equal to the negative of the partial of f in respect to x divided by the partial of f in respect to y. Okay, so these are kind of the rules that we're going to be working with, and we're going to go through examples to show you how these work. All right, so let me switch back to my other so we can go through the examples. All right, so the first example we have is this. We have that w is equal to x squared plus y squared. We're told that x is equal to the cosine of t plus the sine of t. We're told that y is equal to the cosine of t minus the sine of t. And we're told that t is equal to 0. Okay, so for part A of this, is this express dw dt as a function of t, both by using the chain rule and by expressing w in terms of t and then differentiating. Okay, so there's kind of a 2-part situation for part A. So part 1, we want to do the derivative of w in respect to t. So in order for us to do that, here's what we're going to do. And basically what we're going to do is to use that first rule for chain rule. Okay, so we're going to do the partial of w in respect to x times dx dt. Then we're going to add on the partial of w in respect to y times dy dt. Okay, so if we do the partial of w in respect to x, we're going to end up with 2x times. If we do the derivative of x in respect to t, take the derivative of this, we're going to end up with negative sine of t plus cosine of t. Okay? Then plus. Next, we're going to take the partial of w in respect to y. So if we do the partial of w in respect to y, we're going to end up with 2y times. Next, what we're going to do is to do derivative of y in respect to t. So that's going to be equal to negative sine of t minus cosine of t. Okay. Now, in our derivative, we need to be in terms of t. So what we're going to do is replace what x and y are equal to. So in place of x, we're going to put 2 times. We're going to put in the cosine of t plus the sine of t. Then we're going to multiply that by negative sine of t plus cosine of t plus, okay, and kind of ran out of room, so let me move to a new page real quick. So in place of x, we're going to put in cosine of t minus sine of t plus sine of t for that one. Plus 2 times. In this, we're going to put in cosine of t minus sine of t, but we're going to multiply that by negative sine of t minus cosine of t. Okay. So essentially what we're going to do is just kind of simplify this out. So we're going to end up with 2 times. So if we multiply this out, we're going to end up with negative sine t cosine t minus sine squared t plus cosine squared t plus cosine t sine t plus 2 times. And again, if we multiply these together, we're going to end up with negative sine t cosine t plus sine squared t minus cosine squared t plus cosine t sine t. Any questions so far? All right, so if we clean up, we realize that these terms are going to cancel. These terms in this piece are going to cancel. So we're going to end up with negative 2 sine squared t plus 2 cosine squared t plus 2 sine squared t minus 2 cosine squared t. So essentially we just end up with what? We end up with 0. So there's our derivative. Okay. Any questions? Now, the second way of doing this problem, okay, we know that w is equal to x squared plus y squared. And what we're going to do is just go ahead and plug in so we can write w in terms of t and then take the derivative. Okay, so for w is going to be equal to, in place of x, we're going to put in cosine of t plus sine of t. We're going to square that. Plus, in place of y, we're going to put in cosine of t minus sine of t. And we're going to square that. So if we do that, we're going to end up with cosine squared t plus 2 cosine t sine t plus cosine squared t minus 2 sine t cosine t plus sine squared t. So if we clean this up, we're going to realize that this term and this term cancel. And I miswrote. I'm missing a whole big term. Sorry about that. I'm supposed to have another plus sine squared t. Okay. So if I combine what's left, I'm going to end up with the value of just 2. Because I have 2 cosine squared plus 2 sine squared, which is going to be just 2. Now, if I take the derivative of w in respect to t, what will that be? 0. Okay. Any questions? Now, do you keep in mind that there is a value for part B? Well, B, it wants you to evaluate dw dt at the value of t, which is t was 0, but we showed that the derivative is 0, so we evaluate the derivative of 0 at 0, we're still going to get 0. So you can kind of just ignore part B on that since the derivative is 0. Any questions? Okay. All right, next example. All right, so in this example, we're told that W is equal to Z minus the sine of XY. We're told that X is equal to T, Y is equal to the natural log of T, and we're told that Z is equal to e to the T minus 1, and we're told that T is equal to 1. So in this example, again, we want to find dw dt. Okay, we're going to find dw dt. All right, so in this one, we've got 3 variables, so that means that we're going to have 3 terms. Okay, so the first one is that we're going to start off with the partial of w in respect to x. Now we're going to multiply that by what? We're going to multiply that by dx dt. And we're going to add, okay? So the next piece is we're going to do the partial of w in respect to y, but we're going to multiply that by what? Dy dt. Plus, and then last, we're going to have the partial of w in respect to z, but then we're going to multiply it by dz dt. Okay? So let's take a look at this. All right. So if we do the partial of w in respect to x, what will we get? So what would be the partial of w in respect to x? Yes, it's going to be negative y cosine of xy. Then times, now we're going to find the derivative of x in respect to t. We're going to get what? We're going to get 1. Okay. All right. Plus, now we're going to do the partial of w in respect to y. So what will we get for that? Yes, we're going to get negative x cosine of xy times, now we're going to take the derivative of y in respect to t. 1 over t. Okay, and then plus, then the last bit is we're going to do the partial of w in respect to z. And what will we get for that? We get just 1 times. Now we're going to take the derivative of z in respect to t. And what will we get for that? So we're going to get e to the t minus 1. Okay, so now technically this is the answer for this because we have done that. Okay, so now what we're going to do, we're going to leave it in this form. I'm not going to convert it over. All right, so now let's do the part 2 portion of this. Okay, so the part 2 portion is that what we're going to do is to rewrite w. So w is equal to z minus the sine of xy. So what I'm going to do is replace all of these with what they're equal to. Now, we're told that z is equal to e to the t minus 1 minus. We're told that x and y, x is t, y is the natural log of t. Okay, so this is the function now rewritten in terms of just t. So now we want to find dw dt. So what would be the derivative of the first term?
E to the power t minus 1.
Okay, so we're going to have e to the t minus 1 minus. Now, to take the derivative of this, it is going to be chain rule. Okay, so we're going to start off with the derivative of the outside, which is going to be the cosine of t times the natural log of t times the derivative of the angle. Well, it's a product rule. So we're going to do first times derivative of the second plus the second times the derivative of the first. And we can clean this up a little bit. So we have e to the t minus 1 minus the cosine of t times the natural log of t times 1 plus the natural log of t. Okay, so this will be the derivative this way. Okay, any questions? All right, so what we're going to do now is to find out if the values are the same. Okay, so, oops, wrong way. All right, so we said that for dw dt the first time, we said our answer was negative x, let's see, negative y times the cosine of xy plus, or we can do minus, x cosine of xy divided by t. And then our last term is going to be plus e to the t minus 1. Okay. Now, we still have the x's and y's in here, but that's not a problem. Okay. So we know that x is equal to t. We know that y is equal to the natural log of t. And we know that not e, but z is equal to e to the t minus 1. Now at 1, this is going to be 1, this is going to be 0, this is going to be 1. Okay? So if we plug in, all right, so if we take a look at this and do dw dt when t is equal to 1, we're going to end up with negative 0 times the cosine of 0 minus 1 times the cosine of 0 over 1 plus e to the 0. All right, so if we evaluate, we're going to have 0 minus 1 plus 1. So we're going to end up with a value of 0. Any questions? Now, let's just check the other one just to make sure that when I evaluate it at t equals 1, we still get 0. Okay, so for the other one, dw dt, when we did the derivative, we found it to be this expression here. So we're going to have e to the t minus 1 minus cosine of t times the natural log of t, and we're multiplying that by 1 plus the natural log of t. Okay, so if we evaluate this at t equals 1, we're going to have e to the 0 minus the cosine of 1 times 0 times 1 plus 0. Okay, so we're going to have 1 minus 1 times 1, or we're going to end up with a value of 0. So, as you can tell, we still end up with the exact same answer. Any questions? Okay, so let's look at our next example. So our next example, we're going to be dealing with the multiple variables. Okay, so instead of just x, y, and z and t, now we're going to be dealing with x and y, and then in this case u and v. All right, so for this example, we have this. Okay, we're told that w is equal to the tangent inverse of x over y. We're told that x is equal to u times the cosine of v. Y is equal to u times the sine of v. And our point is going to be 1.3 comma 5 or 6. Okay. All right, so the first part of this, okay, we're going to take a look at the partial of w in respect to u. Okay, so we're going to look at the partial of w in respect to u. So in order for us to do this, this is what we're going to do. All right, so we're going to do the partial of w in respect to what variable first? Uh, Not quite v yet. So yes, it's going to be in terms of x times. Now, whatever we have here in the don't do that. What we have here in the denominator must now be in the numerator for the next piece. So we're going to do the partial of x, but now we're going to do that in respect to what? U. Okay, so when you look at this, you see that you've got the partial of u respect to u happening. Okay, then plus. Now we got to deal with the second variable in w. So we're going to do the partial of w in respect to what? Y. And then we're going to multiply it by, just keep in mind that the denominator becomes now the numerator for the second piece. But we're going to do this in respect to what? We're going to take the partial of y in respect to what? It don't want to be v. It has to be u. Okay? So the second piece, because you have to keep in mind that this is our end goal down here. We need the u in the denominator. Okay? Any questions? Okay, so let's take a look at what this is going to come out to be. Okay, so if I take a look at the first piece, so if I take the partial of w in respect to x, okay, so what I'm going to end up with is going to be 1 over 1 plus x over y squared, okay, times the derivative of the inside. So the derivative of the inside is, because if I'm doing it in respect to x, is going to end up being 1 over y. Okay. Now I'm going to multiply that by the partial of x in respect to u. So if I do the partial of x in respect to u, I'm just going to be left with what?
Cosine v.
Sine of v. Okay. All right, so we've done the first portion. Plus, now I'm going to do the partial of w in respect to y. So if I do the partial of w in respect to y, I'm going to have, again, derivative tangent inverse is going to be 1 over 1 plus x over y quantity squared times now the derivative of x over y. So the derivative of x over y in respect to y is going to end up being negative x over y squared. Okay. Any questions there? Now I'm going to multiply that by the partial of y in respect to u. So if I do the partial of y in respect to u, I'm left with just what?
Sine v.
And there's my derivative. Any questions? Okay. Now, again, we can clean this up so that everything will be in terms of u and v. Okay. Any questions there? All right. So the other portion of this is that I'm going to take the partial of w in respect to v. Now, if I write the formula out for this, what it's going to tell me to do is I'm going to do the partial of w in respect to what first? In respect to x. Then multiply that by the partial of x in respect to what? V. Plus. Then for the next piece, I'm going to do the partial of w in respect to what? Y. Then I'm going to multiply that by the partial of y in respect to what? V. Any questions there? Now, with this, for the first part, the partial of w in respect to x and the partial of w in respect to y, it's not going to change. It's going to be the same for both problems. Okay, so for the first piece, it's going to be, again, 1 over 1 plus x over y quantity squared times 1 over y. Now, for the second piece, for the derivative of x in respect to v, now if I take the derivative of x, do the partial of x in respect to v, I'm going to end up with what? So if I do the partial of x in respect to v, what will I end up with?
Negative u sine v, right?
Negative u sine of v, yes. Okay, all right, then plus the partial of w in respect to y, we already know that's going to be 1 over 1 plus x over y quantity squared times negative x over y squared. Now, we're going to multiply that by the partial of y in respect to v. So what would that be?
U cosine v.
Right. So that's going to be u times the cosine of v. Okay. And again, we can clean this up and put everything in terms of v. Right? Any questions there? Okay. So let's really look and see what this actually does to clean up to b. Okay. So what I'm going to do now, all right, I'm going to rewrite, wrong way. I'm going to rewrite w, which is defined as the tangent inverse of x over y. Now I'm going to rewrite that in terms of u and v. So really, this is going to be the tangent inverse of, we said that x is defined as u times the cosine of v. We said that y is defined as u times the sine of v. Okay. So really, this is going to be the tangent inverse of just what? Yes, that's going to be the tangent inverse of the cotangent of v. Okay, so if I take a look at this and look at these, the partial of w in respect to u, what would that be equal to? It's going to be 0. Okay, and then the other one, if I do the partial of w in respect to v, all right, so if I do that, that's going to be 1 over 1 plus cotangent squared, not cosine squared, square root v times, all right, so what's the derivative of cotangent?
Negative cosecant square.
Okay, so we end up with negative cosecant squared of v. All right, so you can simplify this. So if we simplify this, what is it equal to? Yeah, it simplifies down to just -1. So what that's telling us is that if we would have gone through and actually cleaned this up and got it in terms of U and V, this would have been equal to 0. And for this one, if we would clean this up and put it in terms of U and V, we would have got a value of -1. Okay. Any questions? All right. Now, since the derivatives, when you actually plug them in, are going to end up giving you the values of 0, -1, you really don't have to check and see on the other. We can check real quick just to show you. So if I look at this one and do the um, partial W in respect to U, evaluate it at the point 1.3 comma pi over 6. Okay, so if we plug that in, right, we're going to end up with what crazy stuff. Okay, so for x, we're going to have, plug this in, so it's going to be 1 over 1 plus, so in place of x, I'm going to have 1.3 times the cosine of pi over 6 over 1.3 times the sine of pi over 6. I'm going to square that. Okay, then I'm going to multiply by 1 over y. So that's going to be 1 over the 1.3 times the sine of pi over 6. Then I'm going to multiply that by the cosine of pi over 6. Okay, so that's just plugging in that piece. And then we'll do the same for this piece over here. Okay, and plug all this in. Okay, and then it does simplify. All right. In the case of this problem, it probably would be easier to clean it up first before plugging in, just because of the fact that things do cancel and are cleaner. Okay. Any questions? Okay. All right. So let's look at the last one. Example of doing derivatives using chain rule. So for our last example, we are told that U is equal to E to the QR times the sine inverse of P. P is defined as the sine of X. Q is defined as Z squared times the natural log of Y. R is defined as 1 over Z. And the point that we are dealing with is going to be pi over 4. And this point is in terms of x, y, and z. So pi over 4, 1/2, -1/2. Okay, so the first time, what we're going to do is we're going to look for the partial of u in respect to x. So we're going to do the partial of u in respect to x. Now, keep in mind that for this, for the secondary variables, we've got 3. So that means that we are going to have 3 pieces to go with on when we're doing this derivative. Okay, so if we take a look at it, all right, and one of the things I always would encourage when you're doing this is to write out what the rule would be. Okay, so we're going to start off with the partial of u in respect to, all right, so our first variable in u would be what? And just keep in mind, we try to typically go in alphabetical order. So it'll be p, and we're going to multiply this by the partial of p, and we're going to do it in respect to what? X. Then we're going to add on, then we're going to do the partial of u in respect to the second variable would be what? Q. And we're going to multiply that by the partial of q in respect to what?
X.
It's going to be in respect to x, plus, then we're going to do the partial of u in respect to what?
R.
R, times, we're going to do the partial of r in respect to what?
X.
Okay. And yes, it looks long, it looks complicated and everything, but if you look at each piece, if you look at this piece, you notice that these are going to end up canceling each other out. So you've got the partial of u in respect to x. These cancel out, so I've got the partial of u in respect to x. These cancel out, I've got the partial of u in respect to x. Okay, but you just have to do it for each different variable. All right, so if we do that, so if we take the partial of u in respect to p, what will we get?
E to the power QR
Okay,
over square root 1 minus p squared, I guess.
right.
Yeah.
Okay, so it's going to be e to the qr over the square root of 1 minus p squared. Then we're going to multiply that by the partial of p respect to x. So what would be the partial of p in respect to x?
Cosine X.
Yes. Okay. Plus, all right, so now let's do the partial of u in respect to q.
It's gonna be R e to the power QR sine inverse P.
Okay, so r times e to the qr times the sine inverse of p. Okay, now we're going to multiply that by the partial of q in respect to x.
It's gonna be 0.
Yep. Okay, then we're going to have plus. Now we're going to take the partial of u in respect to r, and that's going to give us what?
Q e to the power QR sine inverse P.
Q raised to the qr times the sine inverse of p. Then we're going to multiply that by the partial of r in respect to x?
0.
So, as you notice here, this actually is going to be a fairly nice derivative, okay? So basically what we're going to end up with is equal to, we're going to have e to the qr over the square root of 1 minus p squared times the cosine of x. Everything else is 0. Now, if I go ahead and replace what p, q, and r are equal to, so I can have the e in place of q, I'm going to put x squared times the natural log of y. In place of r, I'm going to put in 1 over z. Okay, over, and we're going to have the square root of 1 minus in place of p. That is the sine of x, but it's going to be squared. We're going to multiply by the cosine of x. So really, what we're looking at is e raised to the z times the natural log of y over. Now, for this denominator, really, what does that equal? Yeah, that's just the cosine of x. And we're going to multiply by the cosine of x. So, these are gone. All right. So, what does e to the z natural log of y simplify down to?
Just y?
Not quite.
Oh, c, y. E to the power z and then y.
No.
No.
Yes, it's going to simplify down to y to the z. Okay. It simplifies down to just y to the z. Any questions? Okay. Excuse me. All right. The next piece that we have is dealing with the partial of u in respect to y. Okay. So what I want you to do first is to write out the formula. But right now we're going to take a short break. So let's do a 10-minute break. And we'll reconvene at 12:15. Okay. All right, so let's continue on. So if we take a look at this particular problem and write out the formula, okay, so we should have partial of u. Let's see here. In respect to p times partial p in respect to y plus partial u in respect to p times, excuse me, not p again. Should be q over the partial of q in respect to y plus, then we have the partial of u in respect to r times partial r in respect to y. Okay. All right. Any questions here? Now, one thing I do want to keep you in mind is that this partial, and this partial are all the same from the previous problem. Okay, so they're not going to change. So for that, the partial u with respect to p, that's still going to be e to the qr over 1, the square root of 1 minus p squared. Okay, then we're going to multiply that by the partial of p in respect to y. In this case, that is going to be 0. Then plus, for the next piece, partial of u in respect to q. That is going to be re to the qr times the sine inverse of p. And we're going to multiply that by the partial of q in respect to y, which is going to be z squared over y. And then we're going to have plus. Then we're going to do the partial of u in respect to r. So that is going to be qe to the qr times the sine inverse of p. And then we're going to multiply that by the partial of r with respect to y, which is going to be 0. So ultimately, this cleans up nicely to give us just r times e to the qr times the sine inverse of p. And we're going to multiply that by z squared over y. Any questions there? Okay, so let's just clean it up. So in place of r, I'm going to put in 1 over z. I'm going to have e. In place of q, I'm going to put the z squared natural log of y times 1 over z. In place of p, we're going to have the sine of x. And then I'm going to multiply this again. I'm going to by z squared over y. Okay, so if I simplify, we know that this expression right here, the e to the z squared natural log of y times 1 over z, that's going to simplify down to just y to the z. What about the sine inverse of the sine of x? What does that simplify down to? Just x. All right, I've got the 1 over z times z squared over y. So that's basically going to simplify down to z over y. Okay, and you can clean it up a little bit better. Let me just rewrite it on the new page. So we have y to the z times x times z over y. So you could essentially rewrite this as x times z times y to the z minus 1. And that would be an appropriate way to write it. Any questions? Okay, so let's look at our last partial. So we're going to do the partial of u in respect to z. So if we do that, we're going to do the partial of u in respect to p times the partial of p in respect to z plus partial of u in respect to q times the partial of q in respect to z plus partial of u in respect to r times the partial of r in respect to z. Okay, so if we look at this, the first one we know is going to be e to the qr divided by the square root of 1 minus p squared. Now, if I take the partial of p in respect to z, what will I get? I get 0. Plus, for the second one, we know that one's going to be r times e to the qr times the sine inverse of p. Now we're going to multiply that by. Now, if we do the partial of q in respect to z, what will we end up with? So if we do the partial of q in respect to z, what will we end up with?
2z ln y.
Okay. 2z times the natural log of y. And we're going to have plus. Then we're going to have q e to the qr times the sine inverse of p. Now we're going to multiply that by the partial of r in respect to z, which is going to be equal to what?
Negative 1 over square root z.
Negative 1 over z squared.
Oh, it's z squared, my bad.
Okay. So it would be negative 1 over z squared. All right. Any questions? So essentially what we end up with is this. We have r e to the qr times the sine inverse of p times 2z ln y plus q e to the qr times the sine inverse of p times negative 1 over z squared. Well, let's clean it up and get it all in one variable. So in place of r, we're going to put in 1 over z. We're going to have e to the we're going to have z squared natural log of y times 1 over z. And we're going to have the sine inverse of the sine of x. And then we're going to multiply that by 2z natural log of y. Plus, next piece is going to end up being z squared times the natural log of y times e to the z squared natural log of y times 1 over z times the sine inverse of the sine of x times negative 1 over z squared. Okay, so in the grand scheme of things, this is what it cleans up to be. This piece here we know is just going to be y to the z. This piece here we know just is x. This times this is going to be 2 times the natural log of y. Okay. This just stays along for right now. This piece here we know is going to simplify to y to the z. This we know is just x. And then we got times negative 1 over z squared. So in the final cleanup, we can write this as 2x y to the z times the natural log of y plus, or actually it's going to end up being minus, we're going to have x y to the z times the natural log of y. So in the grand scheme of things, this is just equal to x y to the z times the natural log of y. Any questions? Okay, so now let's look at the part B of
If you're
it
not
and
vegan,
evaluate
you're
at the
literally
given
contributing
point.
to an animal holocaust.
Okay, so first time,
If you're
we're
not
going to take a look
vegan,
at the
you're
partial
literally
of
contributing.
u in respect to x, and we're going to evaluate it at the point of power of 4, 1/2, negative 1/2. Now, we said that the partial of u in respect to x was, I had to go back a few slides, one too many slides. We said it was y to the z. So we have this as y to the z. So basically it's going to be 1/2 raised to the negative 1/2, or simply 2 to the 1/2, or square root of 2. Any questions? Okay. The next one, if we do the partial of u in respect to y, still at the same point. Now, we said that was equal to xz y to the z minus 1. So xz y to the z minus 1. So we're going to have power of 4 times 1/2 negative, times 1/2 raised to the negative 1/2 minus 1. So we're going to have negative pi over 8 times 1/2 to the negative 3/2, or negative pi over 8 times 2 to the 3/2. I ran out of room over there on the side. So negative pi over 8 times, what are we going to end up with? Basically, that's going to simplify down to 2 square root of 2. So we're going to end up with negative pi times square root of 2 over 4. Any questions? Okay, and then the last one we have, we're going to take a look at the partial of u respect to z. Again, we're going to evaluate at the point pi over 4, 1/2, and negative 1/2. Now, we said that that derivative was equal to xy to the z times the natural log of y. So xy to the z times the natural log of y. So if we take a look at that, in place of x, we're going to put in pi over 4. In place of y, we're going to have 1/2. We're going to raise that to the negative 1/2. And then we're going to multiply that by the natural log of y, so the natural log of 1/2. So we're going to have pi over 4 times basically 2 to the 1/2 times the natural log of 1/2. Or we can have pi times the square root of 2 over 4 times the natural log of 1/2. This is okay, or it could be written as negative pi times the square root of 2 over 4 times the natural log of 2. Because you have to remember that the natural log of 1/2, which is the same thing as the natural log of 2 to the negative 1, is negative natural log of 2. Any questions? Okay. Any other questions? Okay. So next, what we're going to do is the next set of examples, we're going to take a look at doing a tree diagram to help us write out the chain rule formula for the derivative. Okay, so in our next example, we're asked to find dz dt, and we're told that z is equal to f of u v w. We're told that u is equal to g of t, v is equal to h of t, and w is equal to k of t. Okay, so the way we draw the tree diagram, okay, so we're going to start off with the variable that we are doing the derivative of, and we're going to start that at the very top. Okay, now in the middle are going to be the variables that make up the function. Okay, so we're going to put u, we're going to put v, and we're going to put w. And at the bottom, we're going to put the variable that we're taking the respect of. Okay, so in this particular problem, what we're going to do is that we're going to have a branch to here, branch to here, branch to here, branch down, branch over, branch down. Okay, now when we're going from z to u, what that means is what we're doing is we're going to do the partial of z in respect to u. Now, when we're going from u to t, okay, keep in mind that these are defined in terms of functions in terms of t. So we're not going to do a partial, we're going to do the full derivative. So we're going to do the derivative of u in respect to t. Okay, so that's going from z to u to t. Any questions there? Okay, so next, if I'm going from z to v, I'm going to do the partial of z in respect to v. And then when I go from v to t, I'm going to take the derivative of v in respect to t. All right, and the last thing I'm going to do is the outside on the right side. So if I'm going from z to w, it's going to be the partial of z in respect to w. From w to t, I'm going to do the derivative of w in respect to t. So what this tells me is that my formula for dz dt, and I'm just going to follow along the branch. So I'm going to start on the left-hand side, and as I go from z to u to t, basically each line I'm multiplying together. So I'm going to have the partial of z in respect to u times du dt. Now, when I go to a new branch, I add. And I'm going to go straight down the middle. So I'm going to have the partial z in respect to v times dv dt. And plus, and then I'm going to do the right side. So I'm going to do the partial of z in respect to w times dw dt. Any questions? Okay, so let's go to the next example. All right, so in the next example, we're going to do the partial of w in respect to x, and we're going to do the partial of w in respect to y. Now we're told that w is equal to g of uv, u is equal to h of xy, and v is equal to k of xy. Okay, so let's do the tree diagram for the partial of w in respect to x. Okay, so for that particular tree diagram, what's going to be at the top? What variable we're going to have on the top? It's going to be w. All right, so what variables go in the middle? And as far as the middle is concerned, it's just going to be u and v. It's just going to be u and v. And then what variable goes at the bottom? it's going to be x because that's the variable you're taking respect of. Okay. So what we're going to do is follow along this branch to here, and then we're going to go from this side to here. Okay. So if we start on the left-hand side, from w to u, that means we're going to do the partial of w in respect to u. And then from u to x, we're going to do the partial of u in respect to x. Okay. Now, in this, we have to do partials. We can't do full derivatives because of the fact that the function u is made up of two variables. It's not made up of a single variable. So kind of to help you think about when should you use the partial derivative symbol, or should you use the d for the derivative symbol. It depends on how many variables it is for the secondary function. Okay, so if it's only one variable for a secondary function, you can do a full derivative. If there's more than one variable, you have to do a partial. Any questions? Now, on the other side, from w to v, we're going to do the partial of w in respect to v. And then from v to x, we're going to do the partial of v in respect to x. So our formula for doing the partial of w in respect to x is going to be equal to, so if we start on the left-hand side, it's going to be the partial of w in respect to u times the partial of u in respect to x plus. Now on the right-hand side, it's going to be the partial of w in respect to v times the partial of w in respect to x. Excuse me, partial of v, not w, in respect to x. Any questions? Now, without doing the tree diagram, we can write what the partial of w in respect to y would be. Okay, it's going to look the exact, it's going to start off the exact same way. So this top portion is still going to be the same. It's just the bottom verse is going to change because this x is going to change to what? Yeah, it's going to change to y. So if we write this out, it's going to be the partial of w in respect to u times the partial of u in respect to y plus the partial of w in respect to v times the partial of v in respect to y. Okay. Any questions? Okay, so let's look at the last one where we're doing the tree diagram, okay, and draw that one up. Okay, so if we take a look at this, the last example, we have that we want to do the partial of w in respect to s, okay. We're told that w is equal to g of xy. We're told that x is equal to h of r s t, y is equal to k of r s and t. Okay, so when we do our tree diagram, all right, what variable is going to be on top? It's going to be w. What variables are going to be in the middle? X and y. what variable is going to be on the bottom? S. So we're going to have a branch from here to here. Then we're going to do a branch from here to here. Now, here's one thing you have to understand. Even though x and y are defined in terms of three variables, that has no significance, okay? Because we're ending with just this variable here. We don't care about the other variables unless we change the derivative, what we're taking derivative with respect of, and then we'll worry about changing it, okay? So if we take a look at this, all right, for the left-hand side, from w to x, we're going to say it's the partial of w in respect to x. And then from x to s, we're going to say it's the partial of x in respect to s. And then on the right-hand side, from w to y, it's going to be the partial of w in respect to y. And then from y to s, it's going to be the partial of y in respect to s. So when we write out the formula for the partial of w in respect to s, it's going to be the partial of w in respect to x times the partial of x in respect to s plus partial of w in respect to y times the partial of y in respect to s. Any questions? Okay, so I've got just a little bit more to finish up with this section, which is just showing you how to do the implicit differentiation problems. But you can go ahead and start working on the homework for the chain rule. Okay. Also, quiz 8 is available. I think it's quiz 8. Yes. Quiz 8 is available. And it's due on Thursday. Okay. So quiz 8 is available and it's due on Thursday. All right. Any questions? I'm going to look at quiz 8 real quick. Any questions? This one? Okay. If there's no other questions, you are free to go. It's no problem. You guys have a great rest of the day, and I will see you on Thursday.